We continue our discussion of polar coordinates and polar equations by looking at some calculus applications. Our first one is finding tangents and slopes of tangents. The way we can do this is we can think of our polar equation in terms of a parametrization of x equals r cosine theta, y equals r sine theta, and use the derivative slope of the tangent line of a parametric curve that we developed last section. And we have dy dx as dy d theta over dx d theta. If I take the derivative of y with respect to theta, then we have to do the product rule here. We take derivative of the first times the second plus the derivative of the second times the first. And on the bottom we have the derivative of x with respect to theta. Again, this is a product rule. Derivative of the first times the second plus the derivative of the second, which is negative, times the first. So let's look at a problem. The following equation is called a cartioid. Kind of looks like a heart. Find the slope of the tangent line when theta is equal to pi over 3. So we need y and our x. We already have y equals r sine theta and x equals r cosine theta, and we already have dy dx equals dr d theta times the sine of theta plus r cosine theta over dr d theta cosine theta minus r sine theta from above. That's the definition. With this parametrization, you're always going to get that same derivative. So what do we have to calculate? We have to calculate dr d theta. So dr d theta is the derivative of the r with respect to theta. So derivative of r with respect to theta is derivative of 1, which is 0, plus derivative of sine theta is cosine theta. So that's our dr d theta. So dy dx, substituting dr d theta in, we get cosine theta times sine theta plus r. R is 1 plus sine theta cosine theta divided by dr d theta was cosine theta times cosine theta minus r is 1 sine theta times sine theta. If we want, we could factor and combine some like terms. In the top, there's a cosine theta that's common. We can combine then the sine thetas together. In the denominator, it may be possible to do some factoring there as well, but I really don't need to do any of that in order to answer the question. The question is, what is the slope of the tangent line when theta is pi over 3? So I can evaluate this dy dx when theta is pi over 3. So evaluating here for pi over 3, we have cosine of pi over 3, sine of pi over 3, and so on. So perhaps we should draw a unit circle here. Here's pi over 3. That is when the x is 1/2 and the y is square root of 3 over 2. So my cosine of pi over 3 is 1/2. My sine of pi over 3 is square root of 3 over 2. So we have 1/2 times the square root of 3 over 2 plus 1 plus the square root of 3 over 2 times 1/2 over 1/2 minus 1 plus square root of 3 over 2 times square root of 3 over 2. And there we have our slope of the tangent line. Turns out, when you work it all out, this should give you -1.